Okay, I'm going to prove theorem 2.8, the invertible matrix theorems. It's quite long theorems, but this is the most important theorem in a linear algebra. So first, I'm going to prove, here's strategy. Okay, I'm going to prove that, show that if A is true, then B is true. Okay, if B is true, and then C is true. In that way, we end up with this, if K is true, then L is true. Then I'm going to show that if L is true, then A is true. Okay, so we just circle from A to L, and then L goes back to A. So if A is invertible, then B in the statement B is true, which means that A is row equivalent to IN. So that is in theorem 2.7. Is a proof here. Okay. So if A is true, implies then B is true. This is true by theorem 2.7. So please look at 2.7. I covered 2.7 in 2.2. So please look at it. And then if B is true, implies then C is true. So if B is true, then C has n pure position. True. Why? Because this is because the A is equivalent to IN. Then how many pivots in IN? In IN, which is the identity matrix, since what? IN has n pivot position, right? A has n pivot position too. Because A and IN are row equivalent, okay? Pivot positions. Okay, so proof stuff. And then if C is true, then D is true. So C is what? A has n pivot positions, then AX bar equals 0 bar has only trivial solution. Yeah, so why? Because what? Since A is a square matrix, a square matrix, and there are no free variable, right? And no free variable. Free variable. So the set of columns of matrix A is linearly independent. So, and then linearly independent means that what? The AX bar, so linearly independent, let's see, independent, if and only if the AX bar, the system, homogeneous system, has only one trivial solution. Okay, so next one, if D is true, then E is true. Okay, so what's D? E and E is what? The columns of A form a linearly independent set. Yeah, so from I already proved it, right? So I just showed that the matrix A, the columns of matrix A is linearly independent. I just showed it here, so let me skip it. Okay, so see the proof above. Okay, so skip it, and then E, if E is true, implies that F is true. So this is by the theorem 1.12. Okay, so F is what? The linear transformation is 1-to-1. If the the columns of matrix A is linearly independent, then the linear transformation is 1-to-1. Just that is in the statement, is in theorem 1.4. You look at it. Now F true implies the statement G is true too. So F is the linear transformation is 1-to-1, right? Linear transformation is 1-to-1, then AX bar equals B bar has at least one solution, which means the consistent, right? For any B. But actually this is true. Why? Because A is invertible, right? So we should do left multiplication of A inverse, A inverse, A inverse, then X bar will be determined uniquely, right? So, but okay. So, but yeah, let's see. Mm, okay. So since 1-to-1, but we gotta use 1-to-1, right? Okay. Since linear transformation, the T X bar, okay, this is A X bar, okay, is 1-to-1. 1, 2, 1. Okay, 1-to-1. We're gonna use this. This is true, right? So we start from the statement F is true, then G is true. So we use the conclusion of the statement F, which is the linear transformation is 1-to-1. Okay, okay. Then B should be what? Be the image of only one export or any. That means arbitrarily or any, okay? That symbol means arbitrarily or any. For any B bar in Rn space. For any B bar, the B bar should be the image of only one X bar because 1-to-1. So here's the what that means. Okay, so let's say this is the domain. That's the codomain, right? There is a one B bar right here, so B bar here. Then there is only one, the column matrix X bar in domain corresponding to that point, that column vector B bar. There's maybe X bar, maybe. Is there another one corresponding to the B bar? No, then that's not gonna be that, transformation not gonna be a 1-to-1, right? So this is T of X bar. T of X bar. Okay. All right. So now then, okay, B bar should be the image of only one X bar. Okay. So what that means? It means that what? It means that AX bar is equal to B bar has no free variable. Right? What if this system has a free variable? Then this system has infinite main solution, right? It means that there are many, X bars in domain corresponding to B bar. Okay, so that's the uh invalid for the statement. This linear transformation is 1-to-1. Okay, so okay, it has no free variable. Okay, that means what? A has empty but here. Then A has n pivot position. Okay, for each B bar in Rn space. Okay, so now use the theorem 1.4. Okay, so that was the short version of the theorem 2.8. This is short version of theorem 2.8. That was also important. Is really important theorems. I introduced that the last time, right? Here says AX bar is equal to B bar has at least one solution. And this one solution. So by theorem, I mean A has NP1 positions for each B bar if and only if if A has an n position for each B bar, then AX bar equals B bar. This is the homogeneous system, or it could be non-homogeneous system, or it could be homogeneous. Either way, that system has at least one solution for each B bar in Rn space. That's the one of statement in theorem 1.4, actually. Okay. So now in a G, if G statement G is true, then H is true. So see the theorem 1.4. Okay. And then H, if a statement is true, then I is true by theorem 1.12. 1.12. Okay. So GHI, what we got here, G, this is G, and then H and I. These are from the theorem 1.4 and theorem 1.12. Okay. So now next one, I and J. I is true, then J is also true. Okay. What is I and J? I is this. The linear transformation maps Rn onto Rn. There is an n by n matrix C such that CA equals I. Okay, actually this is true. Why? Why is it C? C is A inverse, right? So A, since A is invertible, right? So for each B bar onto Rn, the X bar is what? A inverse times B bar, right? So for each B bar in a, is that what I'm saying? So here's the domain, right? Codomain right there. For each B bar, there exists X bar, and the X bar is actually what? A inverse times the B bar, right? For for any B bar in the codomain, this is Rn space, right? So there exists X bar, which means that the Tx mapped to the entire space of Rn, which means that codomain is equal to what? Our range. That's what the statement says that codomain is equal to Rn. So that means what? Codomain is equal to range. Okay. It means, okay, anyway, so I'm gonna prove it. So, okay, so now T of X bar, okay, is the linear transformation. Maps Rn onto Rn, okay? So even only if the columns A, matrix A span, right, Rn space by theorem 1.12. Right, okay. So this is equivalent to the A has ample positions. Okay, by theorem 1.4. Okay. So this is equivalent to what? Since A has an ample position, which means that what? Ample positions, then A is rho equivalent to I. Okay. A is equivalent to I, then what? There exists the what? Elementary matrix. So then A equivalent rho equivalent to I can be expressed as what? EK times EK minus 1 through the E1. Wake up, sleepyhead. Sorry for the noise. Okay, so let me keep going. Okay, so here, let me, oh, okay. So yeah, so there exists the sequence of what elementary matrices. Okay, so that times A is equal to I, right? So we set that this one is equal to C. Proof is done. C times A equals I. Yeah, that's what statement J says, right? Okay, so what is J? This. Okay, so proof is done. Proof is done. That's a symbol of proof is done. Okay, now J statement J is true implies then K is true. Wait a second, what's K? K is there is n by n matrix D such that A times D equals I. Yeah, D is also inverse matrix. I mean, right multiplication. Okay, it's the right multiplication of the matrix, inverse matrix. Okay, so then from the proof above, I'm going to reuse, okay, recycle the proof in that statement, this statement. Okay, so EK and then EK minus 1 through the E1. From there, what are you going to do? I'm going to multiply the EK through the E1 to the inverse on the left, both sides. So then we got this EK and then EK minus 1 through the E1. And then A is equal to EK minus 1 through the E1 inverse. Definitely this is what? This is going to be identity matrix, right? This is equal to identity matrix. You got it? Yeah, okay. So then A is equal to this, right? So implies A is equal to EK and EK minus 1 through the E1 to the inverse. So now what are you going to do? Actually, purpose is done. Let's say D is equal to 1. EK through the EK minus 1 through the E1. Then AD is 1. Since A turns out to be that this, then when you multiply A by D on the right side, this will turn to what? Identity matrix, right? E1, inverse matrix, in a EK minus 1 through the E1 is equal to 5. Is it? Okay, next one, K implies then L. Okay. So we have to show that what? There exists B, which is in n by n matrix, okay? Such that BA transpose is equal to identity, first one, okay? The second is A transpose B is equal to I, because the statement L is what? A transpose is invertible also. So then we have to show that there exists such a matrix B, B A transpose equals I, and the A transpose B equals I. So from the hypothesis K, this is assumption, right? What's the K? K is what? There exists the matrix D such that AD equals I, right? From that one, I mean, we assume this one, and then we have to show that this one and this. So from the hypothesis K, we can obtain AD. AD transpose is equal to I transpose, right? From the K, right? Implies then D transpose A transpose, because, you know, the property of transpose, this is equal to I. Now what are you going to do? Multiply D transpose and inverse on the left. Then we can get see D transpose, multiply this on the left. What are you going to get? We're going to get D transpose inverse, right? And then D transpose A transpose is equal to D transpose and inverse and I, right? Okay. So now then D transpose inverse and D transpose one turns out to be identity matrix, right? The D transpose inverse is equal to A transpose. So it means that what? It means that A transpose is what? D transpose and inverse. Right? D transpose and inverse. Yeah. And then multiply D transpose on the right we obtain the second one. That was the what? Uh, Give me a second. So oh yeah, okay, sorry. Multiplying D transpose then on the right, then we're gonna get D transpose. Give me a second. Okay. Give me a second. Yeah. D transpose on the right. And D transpose. And then A transpose. You see? On the right in here, okay? We're gonna multiply D transpose on the right side of that one, K minus here. Then we got A transpose D transpose is equal to D transpose inverse times D transpose. But D transpose inverse times D transpose is identity matrix, right? So, well, so A transpose D transpose equals I. Right? So let B be D transpose, then the proof is done. Then what? A transpose times B, which is equal to A transpose times D transpose, that must be equals I, right? Because we show that you see that? A transpose and D transpose is equal to what? I. That's why we set the B as D transpose. Then A transpose B equals I. And then what? B transpose and then B times and B times A transpose was what? We see that this is equal to D transpose times A transpose. This is equal to what? You see that here? B transpose A transpose I. I proved that. So this is equal to I. Thus, B is the inverse matrix. Inverse matrix of A transpose. Proof is done. Okay. Proof is done. Now, last one. If the statement L is true, then A is true. Okay. And since the A transpose is invertible, then there exists A transpose inverse. What does that mean? What is L? Statement L is what? A transpose is invertible, right? Then A is invertible. So we have to show that there exists matrix, I don't know, something so that this times A equals I, and the A times that matrix is equal to I, right? So we assume that L is true, which means that there exists the inverse matrix of A transpose. So we gotta find out this. What is this? What's that? What matrix make this one true? So there is, I think this is that box, that matrix must be A transpose and inverse such that so A transpose times A transpose and inverse is equal to I. It's true, right? And A transpose and inverse times A transpose equal to I. Okay. So since A transpose is invertible, so there exists, inverse of A transpose. I know what that is. Actually, B, right? But okay, anyway. Now what I'm gonna do, taking transpose on both sides for each matrix. Okay. Then A transpose, and then A transpose and inverse and transpose. Okay. See? I mean, taking transpose on both sides here and here. So we got this is equal to I. And how about this one? Taking transpose. Okay, why I? Show. This is going to be A transpose and transpose. You see? We can put transpose in each matrix, right? But we have to reverse the order. So we got A transpose, inverse and transpose times A transpose and transpose. But this is equal to A, right? And then A transpose inverse is what? Inverse matrix of and then this is equal to what? Actually what? A transpose what? This is what? This is I, right? Okay. Or we can say taking transpose on both sides. So transpose of I is what? I. So we got something times matrix A equals I. It means that this is what? Inverse matrix, right? But we have to show the other way. I mean the reverse other way, right? So A transpose. How about A transpose and inverse? I'm going to take a transpose on this matrix too. This one comes from this. Okay. From this. Okay. So there's one. Here's a one. This is two. This is two. So I'm going to take a transpose in second equation. A transpose inverse and A transpose. And the transpose is equal to then A transpose and transpose. And then A transpose and inverse and transpose. Then this is equal to A, right? And then inverse transpose identity matrix is I. So A times something is this. So you see that? This is same as this, right? Right. Thus, there exists what? The inverse of A, which is what? A transpose inverse and transpose. But actually, this is a what? Transpose inverse is commutable. So this is actually A inverse and transpose actually. So this is what A inverse actually. But anyway, so that's the proof 2.8. Please understand all of the statements. Okay, so that's for 2.3.